Welcome back to Mechanical PE Exam Prep. This is Dan, and we're doing 6-minute solutions problem 2. A room is conditioned 75 degrees Fahrenheit and 50% relative humidity. A fan system combines 5,000 CFM of recirculated air from the room with 2,500 CFM of outdoor air at 90 degrees Fahrenheit dry bulb and 75 degrees Fahrenheit wet bulb temperature. The mixed air enters through a chilled water cooling coil as shown. And we have a diagram of what's going on. And they want to know the enthalpy of the air entering the cooling coil is what? So I'm going to summarize some of the given information. You may not feel like you need to do this, but I find it's helpful just to record the givens. We have some what I'm going to call return air conditions. And I'm not really making a distinction between return air and recirculated air, because this air that comes back as returned, which is representative of the room, some of it's getting exhausted and some of it's getting recirculated, but it's the same conditions. So regardless of which path it takes, it all has the same conditions. So I'll just refer to that as RA, return air. And then you have some outside air, which has its own set of conditions. So I'll call that OA. And then there's probably like a physical mixing box here or something, but for all intents and purposes, these two air streams meet and they mix, and then you get mixed air. And that's what hits the cooling coil. So, you know, if the outside air is relatively hot and the recirculated air is warmed from having picked up the heat load from the room, but maybe it's not quite so hot as the outside air, then you have this mixing, and ultimately that's then the coil has to do its thing to get it the rest of the way, to supply whatever the design set point is, and then that's what's going to cool the room. So let's jot down some of what we know. We have the volume flow rate for each path. So for the return air, that's 5,000 CFM. For the outside air, that's 2,500 CFM. The return air temperature is 75 degrees Fahrenheit, and the outside air temperature is 90 degrees Fahrenheit. And it's implied that these are dry bulb temperatures. And then we know the relative humidity of the return air is 50%. And for the outside air, we don't know the relative humidity. Instead, we have the wet bulb temperature, which is 75 degrees Fahrenheit. And what we want to know is the enthalpy of the air, of the mixed air. So let's find the enthalpy of the return air and the enthalpy of the outside air. And then what we can do is we can take a weighted average of those two enthalpies to find the enthalpy of the mixed air. And when I say weighted average, I mean a weighted average by volume, because each stream will contribute according to its volume. So the 5,000 CFM path, the return air, is going to have a more significant influence on the mixed air enthalpy than the outside air, because there's less outside air. And to pick up the enthalpy, we're going to use the psychrometric chart. So let's do each path in turns. For the return air, it's 75 dry bulb and 50% humidity. So 75 dry bulb on the horizontal axis up to 50% humidity. That's about right here. And for the other path, it's 90 degrees Fahrenheit and 75 degree wet bulb. Now when you have the wet bulb and you want the enthalpy, you actually don't need anything else, and I'll show you why. But let's look at this. 90 degrees Fahrenheit. Follow that up. That's this line here. But then the wet bulb is along this curved axis. So it's 75. So to actually find the point, we'd have to find the intersection of 75 and 90, which is right here. But it doesn't really matter, because to find the enthalpy, we have to follow that up along this line of constant enthalpy, because the enthalpy is along here. So we end up having to go through that wet bulb temperature. So if you already know the wet bulb, that basically implies the enthalpy. So I could have just went 75 and then came straight out here. But, you know, helpful to know that these are the 2 points, because for any quality, whether it's, and this is the bigger picture of this problem, whether it's temperature, enthalpy, humidity, whatever the case may be, if you're mixing two streams, then the quality of the mixture must be some point along that line. So that's worth noting. All right, so what's this enthalpy out here? This is about 38.6 BTU per pound. That's for the outside air. And then for the return air, that's this point here. So we're going to follow this line of constant enthalpy out to about right there. And that looks like 28.2 maybe BTU per pound. So now we could kind of eyeball this. We know there's more return air than outside air, so it's going to be about a third of the way up this line. So maybe that's about right here. I haven't measured it. You can do this with a ruler, and then you'll come out here. It looks like about 32, but I kind of cheated. I looked at the answer. So let's actually do the math behind that. So we want a weighted average of these two. So the mixed air enthalpy is going to be 28.2 times the CFM 5000 plus 38.6, which is the contribution from the outside air, times 2500 divided by the total CFM, which is 7500. And if you plug all that in your calculator, you will get 31.7 BTU per pound. So we'll call that about 32. And that is answer B. So long story short, we found the return air and outside air conditions on the psychrometric chart. We recognize that any property of mixing those two streams has to be somewhere along that line. And of course, it's going to be closer to the stream with more volume, which in this case is the return air. And if you want to work that out mathematically, you can do a weighted average. And turns out to be an enthalpy of 32.